Hello everybody, this is Mike Bartles from the Hydrologic Engineering Center. This video is a recording of a webinar which took place on May 25th, 2022. Within this video, several members of the HEC SSP team demonstrate features and bug fixes that will be released within version 2.3. Enjoy! Thanks for joining us today for our first HEC SSP webinar. So my name is Mike Bartles, and I am the HEC SSP team lead. We're gearing up to release version 2.3, which brings bug fixes, enhancements, and quality of life improvements to the table that aim to make statistical applications more efficient and accurate. So within the webinar today, you're going to hear from two other team members and see them present several new and exciting features that they help shepherd through the development process. At the end of the presentation, we have dedicated time set aside for discussion and questions. After I give a brief intro, Dave Margot is going to present several bug fixes and enhancements related to Bulletin 17 analyses. So Dave is a lead engineer with the Risk Management Center, and aside from being an avid fisherman, Dave is a wizard in statistical hydrology and has devised numerous new techniques and methods related to peak flow frequency analyses that have been included within version 2.3. After Dave, you'll hear from Ryan Kao, who is a hydraulic engineer from the Portland district. As you'll no doubt pick up from his talk today, he has a lot of valuable real-world modeling experience that has helped immensely while developing HEC SSP. So if you enjoy using the new record extension analysis that he'll show, be sure to thank him for all the testing he has performed, which got it to this point. I'd like to give a shout out first and foremost to our partners who actually funded us to add these enhancements you'll see today. So the list of partners includes the USACE Science and Engineering Technology Program, the Risk Management Center, and the USACE General Investigations Program. This webinar is being recorded, and the video is going to be posted to our website soon. And everybody should be on mute to minimize disruptions. Please type your questions in the chat. We'll either answer them there, get to them at the end, or we'll email you back. So without further ado, I'll get started. So brief overview of the presentation today. I'm going to give a very, very brief background on the software, like where we've come from and where we're going. I'll also talk about documentation, tech support, and tech transfer before giving the mic to Dave and Ryan, because I would be remiss to talk about any of that stuff in any presentation. So as a brief background, if you go to our website, which I included a link here, you'll find that the most recent release of SSP is version 2.2, which was posted in June 2019. So it was a long time ago. It's been a while since we made a release or an updated version, and that's why we're putting on this webinar today, to get the word out about several new features that we want people to be aware of. We have included several beta releases of version 2.3 recently that have been posted to our website. Most recently, beta 2 has been posted. I plan on posting an updated beta 3 to our website soon. If you're interested in testing these new features, I'd love to have your help and hear about any problems that you may encounter. Please send me an email or an email to the HEC email list, and I'll get you on there and notify you of any new changes that come along. I should note, the beta version doesn't require any admin rights to download or to use. So don't worry about that. You don't have to ask ACEIT for permission. You can use it on your own machine. The HEC SSP documentation has been massively buffed. So no longer are we using static PDFs or anything like that. Everything is live and online. We can update in a moment's notice. Major shout out goes to Matt Fleming, who helped make this happen. Trisha North from the Philadelphia district, major help making this happen. Thank you guys so much for that. You should notice that this documentation looks similar in structure to HEC HMS's. So if you appreciate that, you'll also appreciate this. We stylized a lot of our documentation after that. So if you go to our documentation page, you'll find links for things like the tutorials and guides, user's manual, release notes will be contained within the user's manual, examples, and training that goes along with that too. Tech support has also massively been improved over the past few years through the use of Discourse. So if you haven't used this service before, it's kind of like Stack Overflow for HEC applications. If you have a usace.army.mil email account, you can sign up for a username and password and post questions to any number of application threads. This one here I'm showing is for SSP, but we have threads for HMS, we got threads for RAS, we got threads for all the different applications that you can think of in there. Even if you don't have a usace.army.mil email account, you can still search through the posted questions and answers though. You can get to hear from Google as well. So this service allows users to openly post questions and then moderators to post answers for everybody to see. This is a massive improvement over just emailing questions and answers back and forth, which only, the person asking the question and myself answering it and anybody else who may be on the CC line ever benefit from. Here, this is out in the open. Everybody can see it. Everybody can see what the selected answer is. We can link to previous questions. We can upvote. There's a lot of people asking questions about the same topic. It's easy for us to justify spending time to improve documentation or add new features or things within the software to make it easier here. So please post questions here. I love seeing them happen. Let me talk a little bit about tech transfer. I have a lot of tutorials and guides that have been posted that demonstrate common uses of SSP, as well as new features that we want people to be aware of. This tutorial and guide here that I'm showing an example of is demonstrating a usage of the mixed population analysis in Pennsylvania. However, we have a lot of other cool stuff like study guide and foundational materials that have also been included to explain difficult topics in a more fundamental manner. So like, what is an analytical distribution? What does parametric modeling mean? How does the expected moments algorithm actually work? We have tutorials and guides that explain them in easy to approach styles, right? These aren't very detailed. These aren't very hard and dense to get through. They're meant to be enjoyed and read through relatively quickly. The tutorials and guides also include usage of non-HEC software like R that have also been included to do regression analyses, for instance. We also have lectures and workshops from recent classes that's been posted to our website. So this includes the Statistical Methods in Hydrology prospect course from June 2021 and the Flood Frequency Analysis prospect course from May 2022. So we have 54 YouTube videos that were also created for these classes that are also publicly available. Showing a couple of them here for parametric modeling. They're meant to be easily digestible, quick to watch. You can go backwards in time. You can watch them on 2 times speed if you wanted to go through them even faster. But please use these materials. They're there for you guys to enjoy and learn from. Ask us if you have any questions about them. All right. Enough of me. Now I want to kick it over to Dave to do some explanation on Bulletin 17C.
Yeah, thanks, Mike. So there's a lot of material to cover. So we're going to go through it relatively quickly and at a relatively high level. We're not going to get too deep in the weeds. But this is just to give you a snapshot of some of the changes. And if you're interested in more details, you can follow up some of the resources Mike provided or reach out to one of us if you have specific questions after the webinar. I'm going to talk about 5 things, many of which we've been working with the USGS in a collaborative effort to make some improvements to the implementation of 17C. So I'm going to talk about weighted skew, effective record length, plotting positions, expected probability, and then low outliers or potentially influential low floods. If you go to the next slide, Mike. So we'll start with weighted skew, just a really quick refresher on weighted skew. This is something that's caused a lot of concern for people lately because some announcements have gone out that there's some issues with the current implementation and people should be cautious if you're doing weighted skew calculations. So just a reminder, right, why we do weighted skew. So station skew estimates are really sensitive to extreme events, especially when we have short record lengths, which is often the case. So we use regional skew information to improve our estimate of the skew with a weighting concept. So basically the station skew estimate and a regional skew estimate get combined within EMA to improve our estimate of skew and thus give us a better estimate of the flow frequency curve. Next slide, Mike. So I'm going to summarize the issue in 2 slides. So this just lays the groundwork for what is happening and the cases where it's happening. So I'm going to use this example of a real site. This is data from a real analysis, a core project. And one way you can visualize the issue is to split up the analysis into parts. So on the far left here, we start with only looking at an analysis of the systematic data. The middle plot is the addition of some historical information. So in this case, 1 historic flood event and the remaining historic period defined by a perception threshold. And then the far right is the addition of paleoflood information, which has a fairly long historical period. And it's hard to see on the plot here, but there's one paleo stage indicator estimate for a paleoflood event. So you know, the next slide, Mike. So you'll see the results for those three analyses summarized on this plot here. So just to orient you to the plot, on the x-axis, we use effective record length as kind of a way to measure the amount of data we have, the amount of at-site data we have, right? So moving left to right, the far left is systematic only. Those are the yellow symbols. Systematic plus historic are the blue symbols, and systematic plus historic plus paleo are the green symbols. We have an at-site skew estimate from the at-site data. Those are the squares. So we have a yellow, blue, and a green square for each of the analyses. And then we have a regional skew estimate, which is shown as the dashed black line near the top there. That's our regional skew information. So we basically weight the regional skew estimate with the at-site skew estimate to get a weighted skew estimate. And the weighted skew estimates are the solid circles. So what we should expect to see with weighted skew is as you increase the amount of information, the amount of data that you have at your site, the influence or the leverage that regional skew has on your weighted skew estimate should go down, right? So the at-site information should start to dominate over the regional skew information the more information you have at your site. So as you move from left to right in these analyses, you should expect the weighted skew estimates to generally trend towards the at-site skew estimates. So if you can hit the next slide button there, Mike. So what happens in the current implementation of EMA is kind of the opposite of what you would expect to happen. Instead of the weighted skew trending closer towards the at-site skew estimate, it actually is trending towards the regional skew estimate. And that basically happens because the implementation of equation 720 that's in the appendix of Bulletin 17C overweights the regional skew information when you have censored data, particularly when you have censored data defined by a perception threshold. All right, next slide, Mike. So that's an example for real data. It's a little easier to visualize with some kind of synthetic or hypothetical data. So in this synthetic data, we can generate an experiment where we can basically have the at-site skew estimate be a fixed value, right? So those are the open squares at the top there at about 0.3. In this hypothetical example, we assumed a regional skew value of 0.1. That's the dashed black line. And then the solid circles are the weighted skew. So you see the same issue if you hit the button again there, Mike. The weighted skew estimates are trending in the wrong direction. So as you add really long historical records that are defined by long periods of perception thresholds, you get this incorrect behavior in the weighted skew estimate. So this is the issue that was discovered. When it shows up the most is when you have more historical information and longer periods that are described by perception thresholds. So if you don't have much or hardly any historical information, this is not going to be a big issue. It tends to become a big issue when you have really long records, particularly in some of our applications when we have long paleoflood records that are hundreds to a few thousand years in age. The error starts to get significant. All right, next slide, Mike. So what are we doing to fix it? So, you know, the jury is still out on the final answer, if you will. We're still doing some evaluation and testing of a couple of options, but this is the leading candidate, and this is the option that's in the 2.3 beta of SSP. So this basically uses equation 710, which is in Bulletin 17C. It's listed here. It's a complicated equation, so don't worry about understanding the details of it. If you hit the advance one time there, Mike, there's a term there, the very last term, N sub G times G. That is where the regional skew information gets embedded directly into the calculation of the moments within EMA. So everything to the left of that are the at-site terms. So you have terms for systematic data, low outliers, historical data, expected moments that are associated with perception thresholds, and so on and so forth. So that's all the terms to the left. They each get weighted by their respective number of data for each type. And then we just add to that calculation the regional skew and weight it appropriately with this N sub G, which is representative of an effective record length of the regional skew information. A couple of different ways to estimate that. We're exploring them, testing them. But again, right now the leading candidate is listed there in the second bullet using an equation that was developed by Veronica Griffiths, now Veronica Webster, as part of her graduate work back in the early 2000s. All right, next slide there, Mike, please. So what does it look like when we incorporate the improvement or the fix, if you will? So now this is the same data set I showed before with the three analyses. If you hit it one more time there, Mike, you can now see that the weighted skew estimates, which are the solid circles, are now trending in the correct direction, right? As we add more data, as we add historical information, it trends closer to the at-site skew. And as we add the additional paleo flood information, it continues to track in the right direction, closer to the at-site skew, because we have more at-site information, which means the at-site information carries more weight than the regional skew information, which means that our weighted skew should trend towards our at-site. So this generally fixes the problem. And like I said, there's two or three maybe sub options to this that we're exploring. I think they're all going to perform very similarly. So I'm confident that it's a safe bet to use 2.3 beta for any kind of weighted skew analysis you're using, and things will get finalized as we wrap up our testing. All right, next slide, Mike. Effective record length is the next topic. So just a refresher on what effective record length really is and why we have it and what we use it for. So conceptually, effective record length is we have this data set, right, with some systematic data, some perception thresholds, some flow intervals that might describe historical floods here on the left. We want to find out, or we want to identify an equivalent, at least conceptually, an equivalent set of data that is all systematic, that has some record length, that gives us the same parameter estimates, right? So the same mean, standard deviation, and skew for LP3, and the same uncertainty, right? So the same confidence intervals, if you will. That number of data, that number of equivalent data, is what we call the effective record length. If you go to the next slide, Mike, and this is why we do it this way and how we use it. So there's lots of different stochastic flood models out there. Three examples in the core that are listed there: HEC FDA, flood damage analysis; HEC WAT, watershed analysis tool, I think; and RMC RFA, which is reservoir frequency analysis. So the objective is that the uncertainty that we are going to model in those stochastic flood models should agree with the uncertainty that we computed in our flow frequency analysis. So essentially the uncertainty we get out of HEC SSP or PCAFQ or whatever software you're using. We model that with effective record length typically, at least in these models listed here, right? So the inputs to these stochastic flood models are the parameters of the LP3 distribution and an effective record length. And then the last item there is just, we're not going to go into this in detail, but the methods that are used, at least in the three core softwares listed above, are pretty common. Either parametric bootstrap, which is used in HEC WAT or RMC RFA, or sampling from the parameter sampling distributions, which is how HEC FDA does it. So this is why we do effective record length and how and why we use it in practice. So next slide. So this just shows historically some early concepts on effective record length. So it's convenient that the record length of an analysis, the number of data, is inversely proportional to the quantile variance, which is basically just the uncertainty in the flow at a given AUP, right? So when you think of the uncertainty in your frequency curve defined by your confidence limits, that can be described numerically with a variance number. SSP reports that number, PKFQ does as well. So we can use that proportionality to estimate effective record length. If you go to the next slide, Mike. So we made 2 improvements from that method. One improvement is that assuming the relationship is linear is more accurate than assuming it's proportional, especially when you're dealing with relatively short record lengths. So you can get a more accurate effective record length. And then the other key improvement is that the variance at a quantile, so the uncertainty in your frequency curve, is a function of both the effective record length and the values for the parameters. So you have to hold the parameters constant when you're estimating effective record length. So in implementing this method with these 2 improvements, it's really relatively simple. The equation's a little daunting there, but it's just a linear interpolation. So we can identify 2 points that have the same parameter estimates as our distribution. We can pick 2 record lengths at which we want to estimate the variance. That's all done behind the scenes in SSP. It's relatively simple to do. And then we know the variance for our data from our frequency analysis. So the only unknown in this plot here on the bottom left is the ERL for our data set, right? We can assume an N1 and N2. We can calculate the variance 1, variance 2, and we know what the variance is for our data at a given AEP. So it's just a simple linear interpolation to get an estimate of the ERL. Go to the next slide, Mike. Thought I had maybe one more slide on ERL, but I guess I didn't. But anyway, that's how we get ERL. All right, moving on to plotting positions. So plotting positions, this was just more of a, this is a very, very minor thing, but it was just more of an annoyance for me, frankly. Because I couldn't figure out, early on, I couldn't figure out when you enter data as a flow interval, right? So when you put, say, a historic flood in with a low value and a high value, it wasn't obvious what the software was doing and how it was ranking that flood in terms of calculating plotting positions. So with EMA, one of the key elements for doing plotting positions is you have to know whether or not a particular flood or collection of floods is above or below one of your perception thresholds and what their rank is. So it wasn't obvious what it was doing, and we kind of figured it out by trial and error that it's using the geometric mean of the high and the low value when you enter data as a flow interval. So the issue with that, obviously, is that that wasn't written down anywhere except in the software, and it wasn't obvious to me as a user, so I'm assuming it wasn't obvious to others. But the more important thing is it creates an interdependency, right? So if you're familiar with EMA and how it works, the high and the low value that you enter for a flow interval plugs into the equations for the moments, right, that EMA is using to estimate mean, standard deviation, and skew. And because the plotting positions are using the geometric mean of those 2 values, right, it also affects the plotting positions. So you can get some strange things potentially happen. So our goal was to kind of separate those 2 things and make them independent. So if you go to the next slide, just show a quick hypothetical example here of what I'm talking about and how this works. So in this example, we've entered a flow interval with a low and a high value represented by that vertical bar for some historical flood event. The software as it exists now will currently calculate the geometric mean of that high and low value. In this hypothetical example, it ended up being below the value of the perception threshold. So the software is going to assume that this flood is below the threshold which means that instead of it being the largest flood that's above all thresholds for this entire period of analysis, which is about 1,400 years, it's actually going to assume it's only above the next highest threshold, which covers a much shorter period of time. So you'll get a much more frequent estimate of the plotting position. So if you go to the next slide, you'll see how that shakes out in terms of plotting positions. So, our intuition is, or our judgment from this analysis is more likely to be that that's the largest flood we observed that's above all thresholds over, roughly 1,400 years. But it plots at a plotting position on the order of 200 years because of how that geometric mean calculation affects whether it's above or below the threshold, which then in turn affects the plotting position. So the plotting position here, is out of place from our understanding of the data for this example, which could, lead to some unnecessary concern as far as how good our analysis is here. So if you go to the next slide, Mike. So it's a really easy fix. It's pretty trivial. Now in the 2.3 beta of SSP, the user enters, when you enter a flow interval, you enter a low value, a high value, and a peak value. So the previous software didn't really use that peak value for plotting positions. Now it will. So the user can control exactly what value it's going to use for the plotting positions by modifying that peak value. The nice thing is it makes it independent of any distribution fitting, because the fitting of the distribution, so in other words, the estimate of the moments, only uses the low and the high value. It's just the range. And the plotting position is only using the peak value. So it keeps those two things separate. And it gives the user some more direct control over how they might want to pick a peak value so that the ranking of the floods comes out the way you expect them to. So if you go to the next slide, there's a quick little visual of that. So now the user can specify, as I said, a peak value in the flow range table that ensures it's higher, at least equal to or higher than the threshold. So if you want this flood to rank as the largest flood above all thresholds for the entire period of analysis, you just have to enter a peak value here that is greater or equal to the threshold. In this example, the threshold is about 375,000. So as long as you enter a peak value greater than or equal to 375,000, you will get the desired plotting position. So if you go to the next slide, you'll see how that shakes out. So now it plots in a place that makes a lot more sense relative to the information that we entered into our analysis. If you're interested in details on how plotting positions are calculated, we obviously don't have time for that, but there's a whole appendix in 17C that covers it. And actually, Jerry Stedinger, whose name is half of the name for the Hirsch-Stedinger plotting positions that are used in Bulletin 17C, is on the call, so you could always ask him, and he could probably point you to some good information as well. All right, next slide. Expected probability. So this expected probability thing has been a big deal for the Corps for a long time, dating back to before I was born. The concept with expected probability, another way you can think of it is think of it like your mean estimate of the flow frequency curve in terms of just using simple terms. The reason it's important for us in the Corps is that when we are making risk-informed decisions, which is most of the decisions we make, the expected curve is generally the optimal curve you want to use for risk-informed decision making. Right? So when you're making a risk-informed decision, you generally want to be using the mean estimate, and the expected probability curve is reflective of that. So that's a reason the Corps has been using it for a long time. Bulletin 17C had an expected probability adjustment in it in one of the appendices. 17C did not include it. So I guess we're bringing it back. So we're gonna add it to the software. If you're in the Corps and you need it and you use it, it's there. If you're in an agency that doesn't care about or use expected probability, it's an option that you can, I think, turn off. So you don't have to use it. All right, next plot. So how do we calculate it? I'm sorry. So improvement. So what is expected probability? This kind of leads into how we calculate it. We're not going to go over any of the math, but just conceptually. So you can think of expected probability as the mean estimate of the annual exceedance probability for a given flow. So you pick a flow value. You can look at your confidence limits and intervals as a way to describe the uncertainty in AEP at a given flow. And from that uncertainty, you can estimate a mean estimate of the AEP. So the way we do it in SSP, it's just a simple numerical integration scheme. So think of it like, analogous to like the trapezoidal rule. So the collection of confidence limits and intervals effectively describe an uncertainty distribution in AEP at a given flow. Also, if you look at it the other direction, it describes uncertainty and flow at a given AEP. It works in both directions. And we can just numerically integrate that with essentially something like a trapezoidal rule to get an estimate of the mean. So if you go to the next slide, there's just a kind of a conceptual visual of that. So SSP looks at a behind the scenes, a whole range of confidence limits, way more than that's even shown on this plot. We only showed a handful, so it doesn't get overly cluttered. Normally in the software, the output, it reports one confidence interval. Behind the scenes for expected probability, it computes a range from 0 up to 1 at a relatively fine increment. And then we essentially, at each flow, right, you can take a horizontal slice through those confidence limits and do that numerical integration over AEP and get a mean estimate of the AEP, which is essentially your expected probability curve. So the advantage of doing it this way is your expected curve will be consistent with with the confidence intervals that are computed by EMA, and it will also include uncertainty in the skew parameter. So for folks familiar with Bulletin 17B, you remember one of the limitations in both the confidence intervals and in the expected probability adjustment is it did not, neither one of those accounted for the uncertainty and skew. So with this method here, by directly using the confidence intervals, we can directly incorporate the uncertainty, including skew, in the expected probability curve. So you can see here the red curve would be your computed curve, and then I don't know if you can see it, but the blue curve would be your expected probability curve that comes out of this computation. All right, next slide, Mike. And this just shows you what it looks like in the SSP when you produce a graph as an output, right? So you have your, whatever confidence interval you select shown in green. Typically that's like I forget the default. It's a default, it's either 90 or 95%. I'm drawing a blank here, but whatever the default is. The red curve is your computed curve that's computed directly from the parameters. And then that dashed blue curve is your expected probability curve that's computed off of this suite of confidence limits that SSP will numerically integrate for you behind the scenes. Okay, one more topic and then I'll be finished. This one is probably the most, well, I would bet money, it's the most controversial of the changes. And it's probably the one that still has the most work to do to kind of document and demonstrate and test and evaluate, et cetera, et cetera. So with potentially influential low floods, the current software does some things automatically for you behind the scenes in terms of how it processes the data when it identifies low outliers with the multiple grub spec test. So this is just a visual of what it's doing behind the scenes. So I think this is example 2 out of Bulletin 17C, which is Oristimba Creek, I think. So what happens is it will automatically run the multiple grub spec test. It will identify whether or not there's any low outliers according to the default parameters for that test. It will then flag those and Anything that's flagged as a low outlier gets reclassified as a perception threshold and a flow interval. So two things the software does. One is it will apply a perception threshold at the multiple grub spec critical value over the entire systematic period of analysis. And then each of these green floods in the plot on the right, each of the green squares which were identified as pills, get reclassified as a flow interval with a low value of 0 and a high value equal to the multiple grub spec threshold value. So that all happens behind the scenes. Our concern with this is that when you run this out and start looking at the mean square error of skew, which is important if you're doing regional skew studies and weighted skew analyses, or if you look at the effective record length, which in the core is important to us when we're doing risk analysis, because it's one of the parameters we use in our flood risk models. You get some results that are counterintuitive, and some might argue hard to believe that they're even plausible. So this is just an example here. You can see in this example there's like 82 years of data, 30 of which are PILFs and 52 of which are systematic. So given about 80 years of at-site data, we get effective record length that are on the order of hundreds of years, which just doesn't make a whole lot of sense. So we're still exploring the reasons behind this and whether or not it actually is plausible, or whether it's there's something going on that's producing these odd-looking results. So if you go to the next slide, so the current proposal that's in the beta of SSP 2.3 is to only reclassify the years that have PILFs, because we're censoring the data after the fact, right? So if we have a gauge at this location, our gauge is still able to measure flows, any range of flow, right, from 0 to infinity. So the idea that we're reclassifying or censoring our low outliers does not affect whether or not we could have or would have observed flows, right? We're only reclassifying them after the fact as low outliers in order to reduce the influence or leverage they have on the fit of the upper right-hand tail of our frequency curve. So what SSP 2.3 beta does is it only reclassifies those floods that are identified as PILFs. So in this example, only the 30 years in which PILFs were identified, which correspond to the green squares there on the right, get recoded as flow intervals with corresponding perception thresholds. So you can see the change in the results on the right. You get mean square errors of skew that, are they right? We don't know yet. Do they make more sense? I would argue they make a lot more sense. And then similarly, for the effective record length estimates, which are important particularly for folks in the core, makes a lot more sense. Again, is it right? That's still to be determined. But I think there's a strong case that it's better than what the existing procedure does. So more to come on this as we go through our testing experiments, but this is what's in there now for folks. So again, another key point is that this does not affect the fitted distribution. So I don't know if you noticed it, but the mean, standard deviation, and skew stay the same, right? So it has no effect on your computed frequency curve. The only thing it's affecting is the uncertainty analysis, right? And the metrics that get reported associated with that in the software, which are the mean square error of the skew parameter, the quantile variance, and the effective record length. So if you're only interested in the computed curve, either method will give you the exact same answer. If you're interested in the uncertainty, this method here will give you a more plausible answer for a lot of cases. So with that, that's the last thing I have, Mike, and then I guess we want to move on and do questions at the end, I think, right, to make sure we get through all the presentations.
Yep. I'm gonna kick it over to Ryan now, and he'll talk about record extension. So go ahead and take control.
All right. Let me share my screen here. Okay, so record extension. This is a topic that I think has been a little confusing or intimidating to people sometimes. And with the new features that have been added to SSP, I think it's a lot easier to see what's going on and, yeah, easier to just to perform yourself. So before I'll do a demo of how to do it in SSP in a minute, but we got to talk about what this is to begin with. So the idea is you're doing a flow frequency analysis at a site where you don't have a whole lot of data, for instance, this site on the left, but you do have a lot of other sites nearby. And you may have one that has a whole lot of other years of data with overlap with the site of interest. So the idea is you're going to use the information from this long-term site to improve your frequency analysis at the short-term site. And so I'll start with just a quick overview of what's happening. It's nothing more than a linear regression approach, essentially, where you've got your short-term site is what you want to predict, and you've got your long-term site, which is values that you have to predict that. So in regular, old-fashioned least squares regression, you just draw a line that minimizes the error, or the squared error of all of the points that you have. And then if you were going to move on, you would take your regression line and make your predictions based on the additional data that you have. So easy enough, you build your regression off this period of overlap of 10 years. And then it's tempting to just say, okay, I have all this other data. Let's go ahead and just estimate all these other years. That's not what we want to do. There's some other nuances that we need to bring in before we move ahead with the actual extension. So the guidance for this is all laid out in Appendix 8, the Bulletin 17C. Up till now, you really had to, there's a bunch of equations in there that you would have to do yourself, or there was an R package that you could use to try to do this extension. But now it's in SSP, and it's a lot easier to implement. So the key concept behind this record extension is the idea that we want to have an improved estimate of the mean and variance for our short-term site. So for a regular log Pearson type 3 distribution, you have your three parameters, mean, standard deviation, and skew. You can usually improve your skew estimates by using a weighted skew, like Dave talked about just a minute ago. This is about trying to improve your mean and your variance components of that LP3 distribution. And so the idea is that you're using the full record of the long-term station to help get a better estimate of your short-term station. And these Matalis-Jacobs estimators are really the key to the whole process. But we don't need to care about the equations too much. You can look in Appendix 8 if you want for that. But the idea is that after you do this record extension, as part of the calculations, you're figuring out what should my new mean be for my distribution, and what should my new standard deviation parameter be for the distribution. And this is unchanged between Bulletin 17B and Bulletin 17C, but the implementation is a little bit different. So how it works in the Bulletin 17C is that you develop your linear relationship between your long and short station. You then apply that relationship to a certain number of years to come up with new flow estimates for those years, and then do your EMA analysis on that. And at that point, you can layer on other perception thresholds, regional skew, that kind of stuff. So this is the process here. And this is what is defined in Bulletin 17C. It is a shift from Bulletin 17B, because back in Bulletin 17B, it was called a two-station comparison. You would essentially do your frequency analysis on your short-term station, and then after the fact, change your mean and standard deviation parameters. In 17C, in this approach, you're kind of doing it the opposite. You're actually estimating individual flood peaks for years, and then doing your distribution fitting after that. All right, so this is this move 3. This is the actual technique that is espoused in Bulletin 17C. Move stands for maintenance of variance extension. And it's a kind of a tweaked version of it, custom to Bulletin 17C. The original process allowed you to, once you have your regression equation, you could then apply that for all the years of record that you have. But the problem with that is a situation like this, in this image below, where say you have 20 years of overlapping records, but then you have 100 years of additional record at your long-term site. You can kind of tell that if you were to extend all of these 100 years of your long-term site and then add them to your short-term site, you're essentially just kind of taking the characteristics of your long-term site and shoving them onto your long-term site. So it has a lot more influence than it really should. So this twist that we have is that there's this parameter of NE, the number of allowable years of extension that you come at. So it's based on how well correlated the two sites are to each other. If there's more years of records, concurrent records, this NE also gets larger. But this is really key. This prevents us from extending so many years that our confidence limits become artificially low, and that our distribution parameters aren't overly affected by the long-term site. Okay, so I'll do a quick demo of this, and there are a bunch of tutorials on the site that Mike mentioned earlier. You can go on there and follow for yourself, but my intent here is just to show how pretty simple this is to do in SSP. So I've got a model here with just a few gauges loaded in, annual peak data here pretty close to Portland where I sit. So I'm going to go ahead and make my do record extension. So this folder is new to version 2.3. And we make a new record extension. I'm going to be extending the Oregon City data with this Clackamas River data. And it looks pretty familiar because it's the same data set that was in the slide, but I have about 20 years of overlapping record and then almost 100 years of additional data. So my long record site was Kayla, and I'm going to choose that. My short record site was Oregon City. That's what I want to extend. And I'm doing move 3, Bulletin 17C, and it's 1 per year. We're doing annual peaks. So there it is. There's really not. So here's the data plotted up against each other. Pretty easy to see that here at linear relationship is going to work pretty well. So I hit compute, and there it went. So all these red dots, essentially you can see they're comprising the straight line that is the prediction line for the record extension. And right now it's showing all of the years that we could possibly be extending on there. So from the largest year to the smallest year, these are all the years in the long record that might be extended. So this data tab will look, and yeah, correlation is pretty good. It's recommended that you only do this when correlation is above 0.8. So we're well in that range. We have a good amount of overlapping years. So now I'm moving over to the results tab here, which shows, I'll point out a few things. First is that number of allowable years of record extension. So here, when you round this, it's 26 years. So we're allowed 26 years of extension for this site. And SSP has automatically done that for you. Yeah. So it is extending from 2001 to 1976. Here are the extended records as well as for other years, but we don't actually use these in the Bulletin 7C version of Move 3. We're only going to use these 26 years of data. So that's it. It's done. You can save this to a new data set here. Call it like extended. Good. So now we can see here it is. Got those additional 26 years added on to it. And you can go and do frequency analysis and add in all that other information, your regional skew, perception thresholds, and that sort of thing. So that's pretty simple and really straightforward to do. It's always important to look at your data, and there's some more discussions that we could have on that, but we won't go into that for the interest of time. There's a few other things I will talk about, though. One is, okay, say we were allowed 26 years of record extension, but which of these 26 years should we do? The way that the Bulletin 17C equations are developed is that it doesn't, when you're looking at the effect on the mean and standard deviation, that really shouldn't affect. It doesn't matter what years you pick. Those parameters are going to be maintained, but the skew could be a little bit different depending on which years you choose. So right now in SSP, the default is implemented, which is to just do the most recent years, and that works for most cases. Mike is working on an improvement to this that should be in the release version of 2.3 that actually kind of optimally chooses the best sequence of years to extend for that. And then I guess I'll end with just a couple take-homes. One is that the Move 3 process kind of sounds maybe daunting or challenging, and there's a whole lot of other record extension techniques that you may have used in the past. And this is just to show that from a lot of our real-world data sets, the differences between the different techniques, whether you're doing regular least squares regression or any one of these other record extension techniques, they're usually pretty darn close to each other. So if you had used something in the past and you're going to go use this new Move 3 method, you might think that you're going to get much different results. I would doubt it. Results are going to be pretty similar. And then just stressing the importance of this. This is a really easy thing that you can do to improve your estimate of the frequency curve and reduce your uncertainty in the curve. And it can have a big effect, especially for short record length. So this example just shows for what we were just looking at after we had 20 years to start with, which is not very much to do a frequency analysis. And then we added in an additional 26 years. And the change in the frequency curve is is quite large and would have a pretty big effect if you're looking at something like the 100-year event. So I think I'll go ahead and stop there. There is also the ability to do daily flow extensions. Stop there just since I see that we're running out of time. Mike, you want to take it back?
That works. You can just keep it. That's all good. Thank you for that information. This is, like, I want to stress what Ryan said. This is a really, really simple technique that you can use that improves your estimates of not just flow frequency, but also uncertainty around that fitted distribution at numerous locations. So relatively cheap and inexpensive thing that you can do. Very, very good tutorials online as well that Ryan has created. All credit goes to Ryan for those ones on how to actually choose a site to do this as well, because you have choices there, especially in data-rich environments. So please check those ones out. Be of much help to you. So I want to quickly wrap up, because I know we're coming up on the end. I want to be cognizant of everybody's time and talk about some additional enhancements that are contained within version 2.3 as well. So as you can see, this list here is rather large. There's a lot of new features we haven't released in about 3 years, so there's a lot of stuff that we want to get out and share with you. Of particular importance, I want to note the Bulletin 17 variable time window option. This option allows you to fit an LP3 distribution using Bulletin 17C procedures to either a moving or an expanding time window to show you how quantiles like the 1 in 100 AEP flow, or statistics like skew coefficient, mean and standard deviation, change as data is removed or added into consideration. So, example shown right here for Bushkill Creek in Pennsylvania. You can see that once you include the 1955 flood peak, which was absolutely daunting, you have massive changes in your estimates of what the 1 in 100 flow is. So if you want to see why your flow frequency analysis results changed between 1975, the last time the last flood insurance study was done, and now, you can actually graphically show that. This would be a great thing to show in public meetings to explain why results change over time. We'll schedule future webinars to demonstrate this and other features as well. If you're interested in being notified of those future webinars, please send an email to hec.ssp@usace.army.mil with subscribe in the title or body, and I'll add you to the email list for SSP. You can go to the next slide, Ryan. All right, so summarization, get to questions here. Thank you all again for attending this webinar. Really, really, really appreciate it. Want to answer any questions that did come in, and a couple of good points that were made along the way. There were notes to begin with that I should stress the fact that software like HEC FDA or HEC Watt that do actual Monte Carlo sampling or uncertainty sampling from the fitted distribution, you should not input the expected probability curve. Don't do that. You want to input the actual computed distribution or the fitted curve itself. Expected probability is meant for use if you're not actually doing repeated sampling of that fitted distribution or that curve after the fact to incorporate uncertainty in another way. So if you're using HEC FDA or HEC Watt, please input the fitted distribution. That's the thing to actually use. Definitely want to hit that one point home. We answered a whole bunch in the chat about plotting different curves together. I would recommend that you plot, if you're going to show expected probability, I would recommend that you include both the computed curve, the expected probability curve, and the confidence limits themselves all together. They all show different bits and pieces of information of the actual data and the distribution itself, uncertainty that's going on to that. Please do that one. Also want to hit home the point that you don't have to input perception thresholds like the example that Dave showed with a whole bunch of different ones in there. Please don't do that. All these changes, especially the PILF changes that Dave was talking about, those happen automatically within the software. So no need to go back and rescreen your data or anything like that. That happens automatically for you. Please check that one out. If you're interested in looking at the distribution of uncertainty, Beth has some absolutely amazing slides that show how that can be shown through sampling experiments. Very, very cool stuff. Beth is the master of that one. The flow extension method is simple item for sure. It doesn't include gaining streams or losing streams or other complications like serial correlation and things like that. You'll need to take that into account as you go through your actual analysis. Ryan does have some good tutorials and guides that goes into that description as well, or those effects. Right now, the software only allows you to input one station for record extension. Previous applications like legacy programs like Red Freak from HEC allowed multiple long-term stations. That is not part of the current software. However, I am interested in talking with you about that because that's come up in the past. It would be nice to incorporate a whole bunch of different stations to see which one A is best, or B, if you can combo a couple of stations together to see if you can get better information in there. So thank you guys for the questions. If there's anything else that wasn't brought up along the way, send us an email. We're always here to answer them. Dave, Ryan, do you guys have any closing comments that you'd like to make?
I don't know. Just I would encourage folks to use the new version of the software. It has a lot of really useful features in it and improvements. So.
Great.
None for me.
All right. Well, thank you both for helping me present. Hopefully you guys appreciated it, seeing different faces in the presentation and not just me the whole time. If we didn't get your question again, send me an email about it. I'll get to you. We'll send a link to the materials for those that are on the SSP email list. I'll post all this stuff. We recorded the video. I'll post it up on our website that you guys can check out again and again and again and again afterwards if you would like to. Let me know if you would like to be on the email list. Send an email again to hec.ssp@usace.army.mil with subscribe in the title or body, and I'll get back to you guys. You have a good rest of your day. Thanks everybody for attending.